Good evening, students. Today's topic is grade 11 chemistry electronic configuration. Before we enter into the topic, what is meant by configuration? Configuration means arrangement. So arrangement of, here we are talking about electrons. So therefore we can say that arrangement of electrons. And where we are arranging these electrons? We are arranging the electrons in orbitals. So you are familiar with what is the difference between shells, subshells, orbits, orbitals, etc. So I don't want to go for a revision of this. Just let me tell you, we have 4 orbitals, SPDF, and we should write in small letters. So what is an orbital actually? An orbital is the three-dimensional space where probability of finding an electron is maximum. Let me take an example. Let us take a classroom. Inside the classroom we are having the arrangement of benches like this. So a table is there here and benches are there. Now this is the whole structure of a class. If I ask you a question, where do you find the students here? We can easily say student A here, student B sitting here. So this will be your board. Come to the next line, C, D, E and F. So if I ask you a question, what is the probability of finding students? You will say that this is the probability of finding student A. Here you find B, here you find C, D and so on. But if I ask you the corner of the classroom, can you find any student? You will say that the probability of finding the student is 0. Apply the same thing to this. Now, we know the shape of the orbitals and also the box diagram of these orbitals. This is the box diagram for S orbital and the shape is spherical. Next, P. It can be Px, Py, Pz and the shape is dumbbell. Coming to D, we have 5 orbitals, dxy, dyz, dzx. So I want to tell you small point here. dxy, dyz and dzx. These 3 orbitals orient themselves between the axis. I don't want to go into the different shapes and I don't want to draw any diagrams here. I am just giving you the difference between the first 3 orbitals and the next 2 orbitals of D. dx square y square square we have written here and the last one is dz square. You know, the donut shape orbital or the baby soother orbital, that is dz square. What difference we find here? The difference is, I am putting square in both the case and this is present between the axis, that is between x axis and y axis, xy, between y axis and z axis, dyz, between z axis and x gives you dzx. So these are all between the axis. But the last two, the x square y square is present on the axis. In some other lectures we will see all the diagrammatic representation, but as of now I am just showing you that if you put x square y square, that will be on the axis. That means the double dumbbell shape the double dumbbell shape can be seen one on x and one on y. So if I draw coordinate axis like this, x, y and z, on x axis like this, on x, and this is on y. So one dumbbell, second dumbbell, so double dumbbell D can be written as dx square y square, because on the axis. I just want to show that difference only, but here it is between xy, yz and zx. Z square, again x axis, y and z, one dumbbell. See, another dumbbell is also on z. So how to represent that? We cannot show that in 3 dimensions. So we have a concentric ring representation here. So one more on this, but that is represented as a concentric rings here. So hope I am clear. If you write x, y, y, z, zx, they are present between the axis. But if you put a square like this, x square, y square, then it is present on x1 and on y, the second one. Hope I am clear with this small introduction. Next. See, F is a complex structure or irregular, so we don't want to go much into that. But 7 orbitals are there. 1, 2, 3, 4, 5, 6 and 7. Fine. So with this what we know, in S we can accommodate 2 electrons, and P, each orbital can accommodate 2. Each orbital can accommodate 2 electrons. I am not showing you the clockwise anti-clockwise spin now. After the discussion of the rules of electronic configuration, there I will show you how you are representing clockwise and anti-clockwise spin. Now S orbital can accommodate how many electrons? 2 electrons. P orbital can accommodate how many electrons? 6. And D can accommodate 10 electrons, and F can accommodate 14 electrons. So this is a small introduction about your orbitals. So we can find the electrons at s orbital. So the maximum probability in this will be like this. So electron can be seen in the spherical shape. Similarly P. Next, if you move on to this, there will be some rules for electronic configuration. Here we have 3 rules. Let me write the names of the 3 rules. The first rule of electronic configuration is Aufbau's rule. Aufbau means building up of something. Aufbau, building up of something. Second one, Hund's rule of maximum multiplicity. Maximum multiplicity. See, what is meant by multiples? Pairing, or you can say pairing. Here pairing of electrons. The last rule is Pauli's exclusion principle. See, Pauli, the name. Exclusion, excluded. Something is excluded. Something is different here. What is that different thing? We will discuss in the next concept. Now, let us remember what are the 3 rules. First one, Aufbau's rule. Second one is Hund's rule of maximum multiplicity. Third one is Pauli's exclusion principle, or you can say rule also. Now, let us see the first rule. See, in this Aufbau's rule, before you go to the definition, he has taken the help of a diagram called as Euler's indices. Euler's indices or diagram. First of all, you should know how to draw Euler's indices, then you can write the definition of this rule. Right? Now, I'll give you a simple method how to draw the orbitals. Let me take 1s, 2s, 2p. What I'm doing is, I'm increasing the number of orbitals here. Here I took only one orbital, 1s. Next line I have taken two orbitals, that is 2s and 2p. Increase to one more, 1, 2, 3. So I will take 3s, 3p and 3d. Next 4s, 4p, 4d and 4. So it is going in an increasing order. Now it will become constant. That is 1 orbitals, 2 orbitals, 3 orbitals, 4 orbitals. Again make it constant. Then again we'll decrease it into 3, 2, 1. Hope you have understood this. I am doing an increasing order of orbitals and then decreasing order like this. Next 5s, 5p, 5d and 5f. So going down 6s, 6p, 6d. So 3 orbitals I have written. Next 2 orbitals 7s, 7p. The last one, only one, that is 8s orbital. Hope you have understood this. After this, we need to draw arrow mark. So from where we will draw the arrow mark? Like this. You can use a scale. After some experience or practice, you can draw like this. Now, when you draw the arrow mark, this is the tail of your arrow and this is your head. Okay? Always remember, the tail of this arrow is only the starting point. Hope you are understanding this point. What is this? Don't take from here or go back. What we should do is draw an arrow mark like this. Again draw an arrow mark. So all these will be your starting points. All this tail of this arrow will be your starting points. Hope you have understood this. Next, what we will do now, you started from here, so you are ending. So which is the first orbital? 1s. The energy of 1s is less than. Come from here again, starting point. So next orbital is 2s. Now again go back. Always the tail is your starting point. Now again come. So what you have? 2p and 3s. Next go back. The tail of the arrow mark is the starting point and you got 3p and 4s. Next, again this is your starting point. You got 3d, 4p, 5s. 3d, 4p, 5s. So what I am doing? I am writing the least energy orbital, that is 1s, and we are going on increasing the energy of the orbitals. What we are building here? We are building the energy of the orbitals. From the least energy, we are building energy and going to the higher energy. So remember, Aufbau is building up. So we are writing the orbitals in the increasing order of energy. Next, where is 5s? Here. Again, go back. This tail of the arrow is the starting point. So 4d, 5p, 6s. Come back. This is your starting point. 4f 5d 6p 7s. Again, come back. This is the starting point. 5f 6d 7p and 8s. 6d 7p and 8s. So this is having the highest energy. Hope you have understood how to draw the Euler's indices or Euler's diagram. Again, I'll repeat. Take 1, 2, 3, 4, 4, 3, 2, 1 orbitals in this order. Next, draw arrow marks. And remember, the tail of arrow will be your starting point. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, 8s. In this order you wrote. So this is the order of increasing order of energy of orbitals. Now, you know how to draw the energy of orbitals using Euler's indices. But what this Aufbau's rule says, it says that the electrons are filled in the orbitals in which order? Increasing order of what? Of energy. So this is the rule. Let us take an example. So example, I'll take nitrogen, atomic number is 7. So that means 7 electrons are there. First write 1s because the least energy. Next, going to the second, 2s and 2p. So 2px, 2py, 2pz. How you are filling this? According to the Aufbau's rule, it says first you have to fill 1s. Don't directly write 1 electron and second electron like this. Third electron, fourth, fifth, sixth and seventh. It's a wrong thing. So what you should do always, we have to take in the increasing order. So first electron, second electron, third electron, fourth electron. After this, the next energy, that is 2s, is less energetic. So this is having more energy. So fifth electron I will write here. Sixth we should not write, that we will see in the second rule. So 4, 5, 6 and 7. 1s, how many electrons are there? 2. So I will write here. What does it represent? If I write like this, ns, this is nothing but number of electrons. N stands for principal quantum number. This is nothing but azimuthal, and this indicates number of electrons. Here also 2 electrons, so I have to mention 2. 2s2. Next, 2px 1 electron 1, 2py 1 electron 1, and 2pz 1 electron is written as 1. So hope you have understood this. So this is about the Aufbau's rule. The electrons are filled in the orbitals in the increasing order. That means first low energy 1s, then 2s, 2p in this order. Now let us see the second rule. The name of second rule, what is that? Hund's rule of maximum multiplicity. No, I'll just mention it as Hund's rule here, but the full name Hund's rule of maximum multiplicity. That means pairing, multiples, pairs, pairing of electrons is done only after orbitals are half filled. Only after orbitals are half filled. One more important thing, these orbitals are called as degenerate orbitals. Important term here. Don't simply call them as orbitals, call them as degenerate orbitals. What is meant by degenerate orbitals? Now let me write S. This is 1s. Next 2s. Next I have 2px, 2py, 2pz. See, in this condition, the energy of 2px is equal to the energy of 2py is equal to the energy of 2pz. So these are called as degenerate orbitals. Degenerate orbitals. But here there are no other orbitals, so we cannot compare the energy. So important points: Hund's rule is not applicable to s orbitals. Important rule, what is that? Hund's rule cannot be applied to s orbitals because they are not degenerate orbitals. What is degenerate? The energy of one orbital should be equal to this, like this. Suppose a d you take, let us understand. You have d 1, 2, 3, 4, 5. You know the names also. Maybe 3dxy, 3dyz, 3dzx, 3d x square y square, and 3dz square. Just I wrote in a rough way. In this, energy of xy is equal to yz is equal to zx is equal to x square y square is equal to z square. Hence, we can also call d orbitals are also degenerate. So we can say p orbitals, d orbitals, and f orbitals can be called as degenerate, and this rule is applicable only for p, d, and f. It cannot be applied for s orbital. Now let us get into the rule by taking an example. So take oxygen. Example, oxygen, atomic number 8, number of electrons are 8. Again, follow Aufbau's rule. 1s, 2s, next 2p, next 3s, and so on. Because only 8 electrons are there, we can complete our filling of electrons up to this. So let us write 1, 2, 3, 4, 5. Can we write one more here, which is called as pairing? No. This method will become wrong. Why? Because they have given that pairing of electrons is done only after degenerate orbitals are half filled. What is meant by half filling? Half filling indicates 1 in 2px, 2 in second electron in 2py, third in 2pz. So this is half filled. So what we should do? We should not write in this manner. What we have to do is oxygen with 8 electrons, 1s2, 2s2, 2px1, y1, 2pz1. Now we have done 7. The 8th electron will be written here. That means what we did, we have done pairing of 2px only after filling 1, 1, 1. That is half filling of your 2p orbitals. Hope you have understood the second rule also. N number of examples we can take, but I want to make it simpler, so I give only one example. Let us move to third rule. Police exclusion principle. To understand this, we should have already known about quantum numbers n, l, m, and s. But in a short way, I will tell you that is n is principal quantum number which will indicate the shell, that is k, l, m, n, where n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4. Second one is called azimuthal quantum number, where you are talking about subshells, that is SPDF subshells, and you know the values also 0, 1, 2 and 3. In other class we will have a lecture on quantum numbers. Now I just wanted to concentrate on the spin quantum number. This is magnetic quantum number, and the last one is spin quantum number, which indicates about spin of electrons. Let us take 1s. In this 1s we have 2 electrons. Let us have the axis for the both electron. One electron will start spinning in which direction? In the clockwise direction. You call it as spin. So that means how the clock will rotate in this direction. Same thing, the electron also will spin in the clockwise direction, and the other one will spin in the anti-clockwise direction, or you call it as anti-clockwise spin, opposite to this. In the same orbital, that is 1s, we have 2 electrons. In that single electron, first one that is having a clockwise spin, and always clockwise spin is represented using arrow mark upward. We can write full arrow mark, or you can also take half arrow mark like this. And what is the value for this? It is represented as plus half. Now come to the anti-clockwise spin. The second electron, which is showing anti-clockwise spin, we will write arrow mark downwards, complete arrow mark, or you can also write half in this manner. And here the value of this is plus half in quantum numbers, but here the value will become minus half. So hope you are understanding this. So what these quantum numbers represent? They are representing about your position of electrons, as well as the effect of magnetic field, as well as the spin. So looking at this, what this Pauli's, P-A-U-L-I, Pauli's exclusion principle says. It says that, according to the definition, no 2 electrons can have all 4 quantum numbers same. I'll just simplify this. R, what I can say is, if you are taking an orbital, one electron is represented like this, second electron is represented like this. That means, if you write NLMS, you know, n is equal to 1, this one, n is equal to 1. I'm talking about the first electrons. This is second electron. Now, if you consider 1s2 here, in the first one, n is equal to 1, L is equal to 0, M is equal to 0, and what is the spin? Just now I wrote, if you write like this arrow mark in the upwards, the value will be plus half. Now coming to the second electron, n is 1, L value is 0. See, later in that particular lecture of quantum numbers you can calculate this. Now M is equal to 0, but spin is equal to minus half, because it is showing anti-clockwise spin, arrow mark downwards. So no 2 electrons, that means if you take 2 electrons, no 2 electrons can have all 4 quantum numbers the same. What is different? Spin quantum number is different. That is why exclusion principle, exclusion, something is different. Something is different here, excluded. What is that excluded? spin quantum number is excluded or it is a different thing. So remaining 3 quantum numbers will be the same for these 2 electrons, but the spin quantum number will be definitely different. One is showing clockwise spin, another one is showing anti-clockwise spin. So using the 3 rules, now let us write electronic configuration. There are some exceptions, that is chromium and copper, which are deviating from these 3 rules. But we will discuss normal electronic configuration. First, hydrogen. According to the rule, 1s we have to write, so single electron, 1s1. Helium, write 1s because this is the lower energy orbital. And how many electrons are there? 2 electrons. First electron upward direction, second electron downward direction by following Pauli's exclusion principle or rule. So we have followed 2 rules here. Similarly, if you start writing nitrogen 7, according to Aufbau's rule, 1s, 2s, 2px, 2py, 2pz, increasing order of energy. Now we can apply Hund's rule also. How? 1, 2, 3, 4, 5. Should not pair this here. We have to go with the half filling of 2p orbitals. That is Hund's rule of maximum multiplicity. Next step. Pauli's rule already we followed. 1 in the upward direction, 1 in the downward direction. This is clockwise plus half. This is anti-clockwise minus half. So 7 electrons we have done like this. 1, 2, 3, 4, 5, 6, 7. 2px1, 2py1 and 2pz1. So this is the general information about the electronic configuration. Now, what are the elements or atoms which are deviating from this? We can identify Cr and Cu, which are showing exceptional electronic configuration. See, you know what is exceptions, which is deviating from our normal 3 rules. Chromium, what is the atomic number? 24. Copper, what is the atomic number? 29. If I will write for chromium, the electronic configuration, see, I will write in a simplified version, that is argon in square bracket. So it indicates how many electrons are there, 18. Okay. Now how many are left out? 6. So what we will do? We have to take next 4s and 3d. So if you fill, that is 4s2 up to this 20, then remaining 4 we have to write 1, 2, 3, 4, 5 orbitals and electrons are written like this. Fine. Now there is a simple rule or principle. What is that is, if any orbitals are half filled or they are completely filled, they will get extra stability. Hope you are understanding this. See, 1, 2, 3, 4 we have. One more electron, if it was there here, means it will become half filled. So chromium will get additional stability. So what happens now? So this is not observed actually. To get extra stability, the same chromium now, I'll write like this, because one electron is being excited. You will get 4s1 and 3d5. Hope you have understood this. What is happening? If there is one more electron here, it will get extra stability. For that reason, what it is doing, it is getting an electron from 4s orbital. So that electron is excited to this. So I have written, so exceptional electronic configuration, instead of following the actual rule, what that is, you have to fill in the increasing order of energy. But 3dl energy is less than this, but still one electron is being excited here. Hope you have understood this. So what I will write for chromium, I will write it as argon in square bracket 4s1 3d5. Similarly, coming to copper, what is the atomic number of copper? 29. If you follow the rules, what will be the configuration? Argon 18 and here 4s2, up to this 20 electrons are filled, remaining 9, 3d9. So if I use the box diagrams, so 9, 1, 2, 3, 4, 5, half filled. Then 6, 7, 8, 9. Now the problem comes here. There is no 10th electron. If at all you would have got that, that is nothing but completely filled, it will definitely gain extra stability. For that reason, what happened? The same thing what happened in chromium, the electron will be excited, and this should be expected electronic configuration. But now, what is the actual configuration? Actual configuration will be 4s1 3d10. So 1, 2, 3, 4, 5. Applying the Hund's rule, 6, 7, 8, 9, 10. We have done pairing. So this is second exception. So copper is equal to argon 4s1 3d10. So very important configuration, that is for chromium and copper. So hope you have understood this. So next lecture we will discuss about quantum numbers. Thank you so much.